In our connected world, cryptography becomes more and more important. And whenever cryptography is involved, you have to ask yourself, where do I store my secret keys that are necessary for this cryptography to work? And more often than not, the answer to this question is, well, we store it in the binary because we don't have any other place to put it, and we hope that the attacker cannot extract it from the binary. In this video, we'll see that in some scenarios, this might not be the best idea. I'm Jens from ITK. So this video will be a little bit different from the other videos you saw from us. We'll use screen sharing to show you a little bit more technical details of things, to get a little bit deeper down into what we do every day. So let us know if you like this, if you want to see more of this. And of course, also let us know if you don't like it, so we can put up more content that actually benefits you in the future. So now let's get into things. In this video, we'll see how hard it is to extract a secret from a binary or a firmware, and we'll do that based on an imaginary example. We won't be looking into real firmwares here. We may not do that for security reasons, but just based on a small example based on OpenSSL that I put together. Here we have some headers for the OpenSSL library. We have an error handling function. We have an encryption function and a decryption function. We won't go through that. It's basic stuff. And finally, we have the main function and a hard-coded key. That is our secret. That is our key that we will use in this program to encrypt a string based on AES in CBC mode. So what the main function does is it takes an initialization vector with random bytes. Then we have the plain text here. It is a string. The quick brown fox jumps over the lazy dog. Then we have some initializations. We encrypt the plain text based on the key, based on the initialization vector, and output it to the ciphertext. And the ciphertext is then printed on the console. And to see whether this actually works, we actually also decrypt the ciphertext again and print the decrypted text on the console. So basically a quick hello world program, and what we'll do now is we'll try to extract the secret not from the source code, that's trivial, but from the binary. Before we do that, we of course have to compile the whole thing. So let's just quickly do this. This was source1.c. We need the crypto library included here. We want to strip the binary out of debug information because that's what you usually do in a production setting, and we want to output this whole thing to firmware 1. That compiled successfully. Let's also confirm that it works. It seems to work. There is a ciphertext, which are random bytes. That's the way it should be, and a decrypted text that equals the string that we input there. So now we imagine that we are the attacker, right? We just have this binary. So what can we do with it? Of course, we can have a look at it. We can inspect the bytes of the binary. So let's do just that. Let's have a look at how this firmware looks on the inside. So we do a quick hex dump and we see, well, there is stuff, but we can't really read much, right? There are some things here, but yeah, I don't know if there is a secret or not. So it's hard to get the secret out of there. And actually that's why many people think, yeah, if we put the secret in the binary, if we bake it in there, it's really hard to extract, especially for larger programs than just my little hello world example here. Well, the reality is, if we do it in such a trivial way like we did, it's really easy to extract the secret, and I'll show you how now. So imagine that you have two firmwares or two binaries where you ideally have different keys, right? You want different keys for different devices. You don't want a single key for all your devices. That key would basically be meaningless because one device will be compromised in the future, that's for sure. And you don't want a master secret then that can be used for all other devices. So imagine you have two firmwares that are the same, but with a different key. And to simulate that, I just copied the source code over here. It's the same source code, but the key that is hard-coded is different. You see this here. Here we have 777. Here we have 616161. By the way, these keys are dumb. Don't use these keys. They are not random at all. They were chosen in a way that their ASCII representation is this here, so AAAA, BBBB, CCCC, and so on, so that we in this YouTube video can recognize them faster. So it's a set of different keys, and what we can do now is we run the command from before. Just now we say we want to compile source code 2 to firmware 2. We did that. Okay, so now we have two firmwares here in this directory. Actually, there are a few more, but just those two are of interest to us. And now we want to extract the secrets. And what we can do now is we can just do a binary diff, right? The only thing that should be different between these two is the secret key. So let's do just that. So let's do a diff. We feed this whole thing with the hex dump of firmware 1 and the hex dump of firmware 2. And voila, we see the differences. Surprisingly, there is another difference. The first difference here does not look like much of a secret key. It's some sort of GNU header. The second difference, though, suspiciously looks like the ASCII thing that we saw in the secret key before. So here we have 61616161 for firmware 1, and for firmware 2 we have 77777, etc. And these are exactly our keys right here. So that wasn't so difficult, right? Now you can say, well, it is pretty unlikely that an attacker actually has his hands on two sets of binaries or two firmwares. And this might be true in some cases. And now I show you that even without two of them, it's fairly easy to extract a secret from it if you have the right tools. So in this video, we'll use GDRA for this. GDRA is a reverse engineering tool that was published by the NSA some years ago. And it makes it really easy to look into binary executables. So here we have our firmware 1, and let's fire up this GDRA program. So what GDRA does is it looks at all the bytes and tries to make sense of it, tries to analyze it and put metadata on it so that it is easier for us to know what's going on inside. So let's analyze this based on GDRA. It's already done. So now we see here on the left-hand side that there are some functions that were identified in this byte mess of this ELF executable. And what we see is that there are some functions that could not be identified because the binary is stripped. But then we have some functions that actually have names. And why do they have names? Well, this thing is dynamically linked, right? OpenSSL is a library that is dynamically linked into our binary, so at some point there has to be an interface, and that's exactly what these names here are. And what is particularly interesting are, of course, the encrypt functions, especially the init function, where we probably know that there is a key involved. Right? So when we click on that, we'll get to the disassembly, where the function resides within the binary. Which is a thunk function here, which basically handles the handover to our real library that is dynamically linked at runtime. And here we see that GDRA also found a reference to this function somewhere else. So now we can have a look at where is this function called from. So let's click on that. And on the right-hand side, we have a tab here that actually not only disassembles the whole thing, but also decompiles the whole thing to source code again. Right? It doesn't look as pretty as the thing that we compiled earlier, but it is somehow readable. You see, here's the encrypt init function called, then the encrypt update and the encrypt final function. And in the init function, we can now say, okay, somewhere in there has to be the key. It has to be some parameter here. We don't know which parameter, but that is fairly easy to find out, right? We can just Google it. And then see here the signature of this function, and we see the first argument is a cipher context, the second argument is the cipher type, then the third argument is an implementation parameter, and the fourth argument is the thing that we're looking for. This is the key, right? So if we count here, 1, 2, 3, 4, we know the key is in param 3. Now param 3 is something that is passed to this function from the caller of this function that we're currently in. So we actually have to find out from where this function is called. And yeah, we saw earlier that is something that GDRA provides us with. Right? GDRA analyzed the whole thing, so it knows from where this function is called, and it's denoted here in the xrefs. So let's click on that and jump to this function from which the function is called, and we see this suspiciously looks like our main function. As a reverse engineer, it doesn't really matter whether it's main function or not, but here we see that the function is called, right? And now what is of interest to us is the third argument of this function, which is this here. And this is the key, and that points to the data segment. And guess what resides there? We can click on that. Here we see the disassembly. That is probably not the best representation, so we go to the bytes representation, which shows us the raw bytes of the binary. And here we see there's a byte sequence that suspiciously looks like our key from before. So we have 61, 61, 61, 62, 62, 62, and so on and so forth. Let's have a look at the source code. That's exactly our key. So that's not so hard, right? And the thing that you typically encounter then when you show this to people who are faced with this the first time is, yeah, well, okay, statically putting our key in the binary in plain text is probably not the best option. So let's obfuscate it. Let's put it all across the binary so that these reverse engineering techniques, like I showed you, are harder to do. And I try to simulate that, and I just changed the source code a little bit, right? So instead of having the key in plain text in the binary now, I have a function that is called getKey. And this getKey function has the only job to reconstruct the key out of information that is put all across the binary. So in this case, I kept it simple, and I had a local variable here where there are some random bytes in there, and then we have a global variable that resides in the data segment up here, which are also some random bytes. And my idea was, okay, these bytes do not contain any information about the key, but if you put both together, then you get out the key again. And that is exactly what happens here. So the different memory segments are XORed with each other, and then we have a temporary key. And I went one step further and said, well, okay, if somebody wants to reverse engineer that, then I can do a little bit of more obfuscation, and I just change or flip the uppermost bits and the lowermost bits with each other. So I exchanged them just to confuse the attacker. Okay, so that should do a fine job, right? We no longer have the key anywhere in the binary in plain text. So how would this look in GDRA then? Let's have a look. We have the firmware hidden key here. Let's fire it up, analyze it again, like before. And like before, we have all these functions here. We can go through the initx function. We are again at the thunk function. We would reverse engineer that and go one step up, where we are here in this function, where the encrypt initx function is actually called. And then we can go up one more step. We are in the main function, and this time the third parameter does not point to the data segment. So there is no way for us to immediately get the key. However, it points to a local variable, the local variable 38. And this variable is written in this function here. So we can jump into this function, and we see this is our reconstruction function, right? This is where the XOR happens and the bit shifting happens and so on and so forth. So I could go and reverse engineer that now, But to be honest, that is not the best obfuscation mechanism. I would probably succeed, but there are much better obfuscation algorithms out there. However, in this video, I want to show you that I don't even have to. There could be the best obfuscation there, it wouldn't mean a thing. Because what we do now is we say, well, at some point in time, when you run the binary, the key has to be in memory, right? Otherwise, you could not encrypt anything. The library expects the key in plaintext in memory at runtime. So we do a dynamic analysis. And what we will do is we will try to debug the program at runtime and set a breakpoint right before this encrypt initx function is called. Because at that time, we're confident that the key has to be in memory somewhere. And we'll do just that. So this address here is something we need, so we copy that. Only the last 2 bytes before, because the one here is actually an offset that Gitra puts there on its own. Okay, so now how do we debug this? To do this, you can use the debugger of your choice. I personally use GDB in this case for our firmware with the hidden key. And actually, I don't use vanilla GDB, but I have a plugin that is called Pwn Debug that is used by reverse engineers, pen testers, and also the bad guys, of course, to reverse engineer the programs, and it makes some things a little bit more comfortable to do. So what we can do now is we can start the program and immediately break. That loads the whole thing in memory, so that we can set our breakpoints accordingly. So that's what happens. We're starting our program, we're starting our firmware. The program stopped right at the start. We see all our registers are empty at this point, except for the stack and the instruction pointer. We have the disassembly where we currently are, we have a stack, and we have a backtrace. So now what we want to do is we want to set this breakpoint that we identified earlier, right? So we can do this by running this command and just inputting the address that we identified in Gitra earlier, right? We want to break right here, right at the encrypt initx function. Let's just do that. That was successful. We have a breakpoint now, so we can let the program continue to run until it hits this breakpoint. We do that, and it seems to have succeeded, continuing breakpoint 1. So we are at this breakpoint now. And what we see now is we have some registers. We have a disassembly around our current instruction pointer, which resides right at this address. So here. And we see we are right about to call the encrypt initx function. And this Pwn Debug plugin actually has the feature that it already knows the parameters, so that makes it much easier in this case to identify that the 4th parameter is the key here. So this is a pointer that should ideally point to the key. However, if we didn't have this, we could easily just look up the manual of the architecture and see where our compiler puts the parameters, and then we would see, okay, parameter 4 that we're interested in, that we know from Gitra, is stored in the register RCX, and this should also point to the secret then. So now let's verify that this is indeed the secret. Let's do a hex dump, not of this address, but at this pointer here. Let's do this. And here we see we have our secret again. Right? Even though we did all this obfuscation, we didn't even have to break the obfuscation. We just had to run the program until the secret is in memory and can be read out. And we did just that. Okay. So to be fair, this whole demonstration relied pretty much on the fact that we had a dynamically linked binary, right? You see here we have the interfaces to the OpenSSL library. So one could argue that if we're talking about embedded systems where things are statically linked, then it's a different story, right? Because it's much harder to identify where the encryption actually happens, where the crypto actually happens and where the key is actually in memory. And actually that is a valid point. So however, there are still, of course, things that you can do about this. To demonstrate this, we have another example, this time not based on an OpenSSL library, but on the embed TLS library, which is a pretty prominent library in the embedded world that is used for embedded devices and that can be statically linked. In this case, the example is a little bit smaller than before. We again have our hard-coded key in there. We have a main function, an initialization vector that doesn't make sense because it's not random, and the input, and then an output, and then we basically call the method setKey, where we say, okay, this is the key, and then we say, okay, please encrypt the input based on AES in CBC mode and write the result to the output variable. That's it. And now we want to have a look at what happens if we compile this binary, strip all the debug information from it, and how would this look in a reverse engineering tool like Ghidra. Let's have a look at that. So I prepared this, it's here, it's called stripped. So let's fire this up and see what Ghidra makes of it. And as you can see, at first sight, it looks pretty similar to before, but once you look at the function tab, Ghidra was able to still identify the functions, still knew that there are functions because of the prologue and the epilogue in those functions. However, it doesn't really know semantics, right? It doesn't know what these functions are doing, so it just assigns numbers to them. And if you try to dig a little bit deeper here, these are a lot of functions. So what I could do now is I could go on and manually analyze them and see whether anything sticks out, whether I recognize an encryption library or an AES algorithm. But yeah, that would probably be wasted work because there are much more efficient methods to do this. And one method I'd like to showcase here is that there are approaches out there that calculate signatures over compiled libraries, so that these libraries can later on be recognized in other compiled binaries. And this can be pretty much automated because you can download all the libraries and compile them on different architectures and calculate your signatures on them. And actually Ghidra is able to do something with these signatures. It can basically unstrip your binaries. It can say, well, okay, I recognize this byte pattern. This is function XYZ. Yeah. And we'll do just that based on our database, which includes public or prominent or often used cryptographic libraries. So I think I have to do this here and then say one shot and function ID, which basically now takes the library that we have and throws it at this stripped binary. So let's do just that and see what happens. It takes some time, but as you can see, something happens here, right? There are still some functions that could not be identified, but a lot of functions could be identified now. There are suddenly names on this. So let's check whether there's anything in there for embed TLS. And yes, there is. So here is a set of functions that says embed TLS AES setKey _ enc. That's interesting, right? So let's have a look at this. Here we have the disassembly. Again, we see that this function is called from somewhere. These are all calls from inside the embed TLS library, and here is a call from outside the embed TLS library. So let's click that, and we see here in the decompilation that we are probably in our main function now, which is not something that the attacker would know. We know because we saw the source code. The attacker probably doesn't know. Actually, it's not important because now the attacker sees, okay, embed TLS AES setKey enc is called with something that points to the data segment again. And now, guess what is there? Probably the key, right? Let's look at the bytes, and guess what? It is our key again. So in this case, we started off with a completely stripped binary. It was a complete mess. It would have taken ages to reverse engineer that by hand, but with the modern tools, it's actually doable pretty fast. So take-home messages. What did we learn in this video? Well, for one, we learned that storing secrets in binaries is not as secure as you would think. Whether this is okay for your device or not actually depends on your scenario, on your attacker model. Are you assuming that the attacker is not able to get his hands on the firmware in any way, be it by physical extraction or be it via software vulnerability to read it out remotely? Then you're probably fine. However, if you're not sure about this, then you probably have to do something. And what is also clear, regardless of what the answer to these questions is, never ever store master secrets on your devices. It is bad practice and it will lead to complete security failure if one device is compromised. So never do that. So what can we actually do? Well, for one, you can start to think about how can you try to make it harder for the attacker to extract the firmware in the binary. Maybe store it in a highly integrated system on chip where it's hard to get the firmware physically out. Don't store it on an external flash memory chip that you can just read out on the PCB or something like this. The other thing that you can do, of course, is you can also use hardware security modules or TPMs, trusted platform modules or something like this. So things that are specifically designed to store your secrets in a separate space from your microcontroller or from your main system. And that has the additional advantage that even if the software is compromised or there is some bug, some vulnerability in your software that allows a remote attacker to read out arbitrary data, your secrets are still safe. You can also think about whether secrets are actually necessary. Just because you use crypto doesn't mean you have to put secrets on your device. For instance, if you just want to distribute an update to a system that is signed, your device does not need a secret. It just needs a public key. You can use asymmetric cryptography for that, where you have a private key and a public key, and the private key is somewhere in the cloud, somewhere at your computing center, while the public key resides on your devices. And the public key is public, so the attacker does not gain much by just compromising your firmware. So there are many things to do. What is applicable in your scenario? I don't know. It highly depends on your scenario, so you have to think about this in the concept phase and act accordingly. That's it basically from my side. I hope you benefited a little bit from this video. For me, it was a lot of fun to do this format. Again, let us know what you think about it in the comments, and you have a nice day. Bye-bye.